Okay, so what questions do we have from the homework? Yeah. Number 12. Oh, the last one. That's really a review problem, but it's a good one to do. So yes, number 12 says, shown to the right is the graph of the derivative of some function g. In other words, it's a graph of g prime. Guys. So this thing is a graph of the derivative of some function. It's the derivative of g prime. And part A says, identify the x coordinates of all relative minimums and maximums of the original function g of x, which is not shown. Be sure to include boundary points. Well, so you might remember that minimums and maximums can occur at two kinds of places: critical points and boundary points. Boundary points are pretty unusual. We haven't done much with them, but I threw them in this problem for funsies. So let's think about critical. Well, okay, let's do boundary points. Obviously, the boundary points are -4 and 5, right? That's where the function sort of ends. Okay, fine. So those guys could be mins or maxes. Critical points are the other places that you could have a min or a max. A critical point is, of course, a place where the derivative is 0 or undefined. And this, of course, is a graph of the derivative. So where is this graph 0 or undefined? Here at -2 and here at 4. That's where the derivative, this graph, is 0. Are you with me? Okay. So, we've got these 4 interesting points, the 2 boundary points and the 2 critical points, and we just sort of need to classify them. Let's start with the critical points. I think they're a little easier. So what's going on here at -2? Well, you kind of want to think about a sign analysis of the first derivative, right? If you want to classify a critical point as a min, max, or plateau, then you really need to do a sign analysis of the derivative. Like, you sort of have to ask, is the derivative positive or negative on either side? And that sort of tells you whether the original function is increasing or decreasing, which in turn sort of tells you what kind of point you're looking at. At -2, you can see that to the left of -2, the derivative, that is this graph, which is shown, the derivative is positive to the left of 2, right? The graph is above the x-axis. And to the right of -2, the graph is still positive, okay? If you like, you can kind of make a little sign analysis here. Here's -2, and to the left of -2, g prime is positive, and to the right of -2, g prime is also positive. So what kind of a point is -2? It's a plateau, because the original function g, not shown, the original function g is increasing both before and after -2. That's neither a min nor a max. It's a plateau, okay? But then if you consider what's happening, over here at say 4, the other critical point, well, just before, to the left of 4, the derivative, this graph, is certainly positive, and to the right of it, the derivative, this graph, is negative. So the derivative switches from positive to negative. In other words, the original function switches from increasing to decreasing, which means that the original graph has a local maximum at that point. Is that okay? Local max of 4. As far as the boundary points are concerned, well, what's going on at -4 over here at the left boundary point? Well, the derivative is positive on this region, which means the original function is increasing. If the function starts at -4, like if it starts being defined at -4, and it has a positive derivative, that means that it's increasing from that point, and that's a local minimum. Can you see that? It's the smallest value in the neighborhood. And then at the right boundary point at 5, well, if the function stops being defined at 5, and just before it reaches 5, the derivative is negative, that means that the original function's decreasing on that little region there, and that would also be a local minimum. Cool. Okay. And then part B is find all the intervals where the original function g is concave up. Well, remember, concavity can be understood on several different levels. Let's just review what they are. Concave up at the level of the original function you know, it just means G looks like this, right? G being concave up just means the graph looks like a happy face. At the level of G prime, it means that G prime is increasing. And at the level of G double prime, it means that G double prime is positive. So you can analyze concave up or identify concave up at any one of those levels. But since we have a graph of G prime, we should probably be analyzing it at this level. Does that make sense? The function, the original function G, will be concave up when its derivative is increasing. Well, here's a graph of the derivative. So when is this graph increasing? I think just on this region here. And that's it. That's where the original function is concave up. Is that okay? What else? Yeah, I could go over 8. So 8 says, consider the function f of x equals sine of x, graph to the right. Find a shaded area by computing the appropriate integral by hand. So what is this thing? It looks like it's the area under the curve from 0 to, if you're kind of sloppy, you might say it's 3. If you notice, though, they say, hey, look, that x-intercept is not exactly 3. It's a little past 3, a special number just past 3. They're talking about what? Pi. They're talking about pi, right? So yeah, this region, it's the region underneath the graph of sine of x from 0 to pi. So that's the integral that you want to compute. Integral from 0 to pi sine of x dx. Now, how do you compute that? Well, you need to find an antiderivative of sine of x. This is using the fundamental theorem. What's the antiderivative? I think it's negative cosine. So negative cosine x, that's the antiderivative, right? Because derivative of regular cosine is negative sine. So derivative of negative cosine is positive sine. And you want to evaluate this thing from 0 to pi. So that's just, you got to be careful with the minus signs. This is negative cosine of pi, right? So my function evaluated at the top number minus my function, which is negative cosine, evaluated at the bottom number. Gotta watch out for that double minus sign there. What's up? Are we good?
Yeah, we're good.
Okay. Cosine pi is -1. So opposite of that is +1 minus cosine of 0 is 1. This minus makes it a -1. This minus makes it a +1. So I think you get 2. By the way, a quick note on this stuff, like this minus sign stuff is kind of annoying. If you have something like, let's say that you're doing an integral and you have an antiderivative, like let's say 3x squared, and you want to evaluate that from whatever, 2 to 5, okay? You can view this as 3 times 5 squared minus 3 times 2 squared. That's a perfectly fine way of doing it. But if you haven't noticed this already, that's the same thing as just sort of keeping the 3 on the outside and then just sort of like doing the evaluation of the variable part alone. So like 5 squared minus 2 squared. So the point that I'm making is that when your antiderivative has a constant multiple in front of it, you sort of can just apply it to the entire evaluation instead of distributing. And that's particularly nice when you have like a minus sign. So like if you have opposite of x squared and you want to evaluate that from 2 to 5, yeah, you can view that in the way of, you can say, oh, I take opposite of 5 squared and then I subtract opposite of 2 squared. You can do that, but it's kind of confusing with all the minus signs. It's better instead to just kind of say this minus sign is essentially multiplication by -1. I can just say that's going to be the opposite of, and then apply the evaluation just to the variable part. 5 squared minus 2 squared. Do you see that that's like much easier to simplify? And so that's how, you know, like this problem here, I had all these minus signs. I really didn't have to. I could have just viewed it as, you know, like negative quantity cosine pi minus cosine 0. And I think that would have been a lot more clear. So good. Could do one more question if it's fast. Anyone's got one? No. Okay. I don't have a lot to say. This is like a super short lesson. Okay. The topic, and this is the last topic that we will do before the mid-year. The topic is average value of a function. Okay, so this is a definition. The average value of a function f of x is defined as, sorry, I need to be more clear. The average value of f of x over an interval a, b, excuse me. We can only define the average value of a function over a specific interval. Sorry about that. So the average value of the function f of x over the interval a, b is defined as, and this is a definition, 1 over b minus a times the integral from a to b f of x dx. And that's kind of it. That's like the end of the lesson. And I'll do one example. There's not a lot to say. So in one sense, you might say, like, why is it that this expression gives the average value of the function? Like, why? And I could respond, well, I don't have to explain anything because I've defined the average value as this object. Definitions don't require necessarily any explanation. You make a definition, it's true by definition. I'm defining the average value to be this object. On the other hand, that's not a very satisfying explanation. Some years I've done some examples and kind of gone into the weeds talking about why exactly the integral somehow has something to do with the average value. It's not really worth it. It's a pretty complicated explanation. And at the end of the whole explanation, I don't know, it doesn't leave you any better off. It doesn't help you solve any of the problems. Very roughly speaking, though, this guy, in some sense, kind of gives you, well, it's the area under the curve. And if you divide by b minus a, that's dividing by the width. And in a sense, that kind of gives you the height. But it gives you the average height, which is the average value. And I think that's about all that I'll say. This is the area under the curve. This guy right here, b minus a, that's the width of the interval. So if you take the area and you divide by the width of that area, you essentially get the height of that area, but it's kind of an average height, which is the average value of the function. That's a very sloppy explanation. And like I said, I could say something a lot more rigorous, but it's not really worth getting into. So I'll just do one example. Average value can be surprising. Let's find the average value of the function 9 minus x squared over the interval -3 to +3. So it's really as simple as plugging into the formula. There's nothing more to it, really. Okay. So what's the formula again? It's 1 over b minus a times the integral from a to b f of x dx. That's the average value of the function over the interval a to b. What's a in this case, guys? -3. And b? +3. Okay, so you just got to plug it, right? So this is 1 over 3 minus -3 times the integral from -3 to +3 of our function, which in this case is 9 minus x squared dx. And whatever this thing comes out to be, that's the average value of the function over that interval. So 1 over, this is 3 minus -3, that's 1 over 6. And to compute this integral, of course, what I need to do is I need to find an antiderivative for 9 minus x squared, which is pretty easy. That's 9x minus 1/3 x to the third. Is that okay? That's the antiderivative. And I need to evaluate that thing from -3 to +3. And yeah, so let's do that. Notice that I've got this 1/6 multiplying on the outside. I'm going to make use of the comment that I made just a moment ago. Like I can view this as 1/6 and just like keep that on the outside and do all the evaluation here and multiply the whole thing by 1/6 instead of having like 2 copies of 1/6. So, okay, so what do? I plug 3 into this function. So that's 9 times 3 minus 1/3 times 3 to the third. Minus, and now we have to be careful, it's supposed to be minus this entire expression evaluated at -3. But if you're going to subtract this entire expression evaluated at -3, you better make sure that that minus sign is applied to both terms. Okay, which could be done, I guess, by using another set of parentheses. So minus quantity 9 times -3 minus 1/3 -3 to the third. A lot of minus signs here, guys. Don't mismatch your delimiters. You know what I'm saying? You know what I'm saying? I feel like if you program a lot, you're probably in good shape with all these parentheses. Okay, well now we just need to clean up this bad boy. So what is this? This is 1/6 bracket. 3 times 9 is 27. Minus 3 to the third is 27 divided by 3 is just 9. Minus, and then what's inside of here? It's 9 times 3 is -27. And then minus, oh my God, okay. -3 to the third is -27 times -1/3 is +9. Yeah, all right. So many minus signs. It's out of control. Well, so that's 1/6. Let's see what's going on here. I got 27 minus 9 is 18. -27 plus 9 is -18. But then it's minus -18. So it's actually plus 18. Okay, so it's 1/6 times 36, which is 6. That was really an you know, I mean, it reminds me of these problems we give you in middle school. That's just like order of operations problems. We just give you like a paragraph of stuff like this and we're like, clean it up. Well, now we can finally justify giving you problems like that. Okay, so that's the average value of the function. Now let me show you, are we okay with that? Do you have any questions on that? I'm basically done. I just want to say average value can be surprising. Like it might not be the number you're expecting. Here's a graph of that function we just looked at. Oh, come on now. Don't be totally wiped out here. There we go. This is 9 up here at the top. Let's see if I can make this thing focus. What button focuses? Not that one. Not that one. Oh, there we go. Look at that, huh? It's nice and crisp. So it goes up to 9, goes down to 0. And so from -3 to 3, this is what the function looks like. And they're saying the average value is 6. I'd say I'm kind of surprised by that. Doesn't that seem a little high to you? It is kind of surprising. The average value can be like not exactly what you're expecting. One thing that I would say is that most of the time, from -3 to 3, most of the time, the function's actually more than 6. Do you see that? It's only below 6, like over this little interval and over this little interval. Most of the time it's above 6, okay? But when it's below 6, it's way below 6. Do you see that? When it's below 6, it's very far beneath 6. And so even though most of the time it's higher than 6, when it's below 6, it's very far below 6. And those two forces kind of balance out. And anyway, it's very hard to guess the average value just by looking at a picture. I find it to be pretty deceptive. Okay, any questions before we start the worksheets? Okay.